Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Irfan bin Muhammad Riaz. Now I will be presenting for my final year project proposal, which is the finite element modeling for the ultrasonic assisted milling of borosilicate glass. My supervisor is Sir Muhammad FAUZI bin OTHMAN, and my co-supervisor is Professor MADYA Dr. JURI SAEDON. The content of my presentation includes the project summary, problem statement, objectives, project scope and limitations, literature review, methodology, expected results, and the references. Now I will look at the project summary. Machining of brittle materials is common in the manufacturing industry, but few modeling techniques are available to predict material behavior in response to the cutting tool. Ultrasonic assisted milling has an outstanding performance in machining hard and brittle materials such as glass. This is a very useful process where machining of hard and brittle materials becomes very difficult, or in some cases it is impossible to machine these materials by conventional methods. In this study, the ultrasonic milling process on the borosilicate glass will be investigated by using finite element modeling to understand the effects of ultrasonic assisted milling in the machining process. Move on to the background of study. Ultrasonic machining is a non-traditional process in which abrasives contained in a slurry are driven against the work by a tool oscillating at low amplitude, which is 25 to 100 microns, and high frequency, which is 15 to 30 kHz. Ultrasonic machining is the best suited process for those materials which have a hardness of more than 40 hardness Rockwell C, and also the workpiece material may or may not be electrically conductive or may also be fragile. Some of the advantages of ultrasonic machining includes reduced cutting force, reduced cutting temperature, reduced residual stress in the workpiece, improved surface quality, improved cylindricity of turning workpiece, and improved cutting stability compared to conventional methods. The tool in ultrasonic machining is made to vibrate with high frequency onto the work surface in amid the flowing slurry. It is stated that tool wear under different cutting conditions is reduced up to 80% by applying the ultrasonic technique. For the problem statement, in most of the industries, machining of brittle materials are becoming common and frequent. Unlike ductile material cutting, which is dominated by shear deformation across shear plane, brittle material cutting is driven by fractures. High cutting temperature in machining processes of brittle materials is another problematic issue and places negative influences on machining performances. Thus, a finite element model on the ultrasonic milling of borosilicate glass will be developed and studied in this project to analyze the effects and overcome the problem. The objective of this project is first to model an ultrasonic assisted milling process on borosilicate glass using finite element model. The next objective is to investigate the effects of ultrasonic assisted milling process on borosilicate glass. And the last objective is to validate the ultrasonic assisted milling model with the results of a journal article. For the project scope and limitation, the scope of this study is focused on creating the suitable finite element model that can undergo the machining process where the tool is able to cut the workpiece as intended. The workpiece with the properties of borosilicate glass will be used in the finite element modeling. There are several limitations or considerations that needed to be focused in order for the finite element modeling to be successful, such as the type of material, the design or shape of the tool, the input parameter used in the finite element model simulation, the response parameters such as the cutting rate, cutting force, and the chip formation. Move on to the literature review. The first literature review is on the finite element modeling. Finite element modeling is the simulating process to determine the response parameter of the machining process, such as the cutting force and chip formation, so that it can be assessed using the finite element method. Finite element modeling consists of two components, which are pre-processing and post-processing. Mesh size and order is crucial to create a balance between accuracy results and runtime. In pre-processing, the main focuses are to assign the type of element, insert material properties, use appropriate mesh element, and apply boundary conditions in the form of load and structures. In post-processing, the main focus is to generate the desired output or results such as the cutting force accurately. The next literature review is on the finite element modeling in machining of brittle materials. Research on the fracture-based finite element model named Embedded Cohesive Zone Finite Element Method was done. To deal with fracture problems, the cohesive element has been developed for finite element model which forms the cohesive zone in the model. In the finite element model, a network of cohesive zone elements are embedded in the material body with regular elements to capture multiple randomized cracks during a cutting process. The cohesive zone concept links the microstructural failure mechanisms to the continuum fields. The result shows that the finite element model can capture various chip forms such as dusty debris, irregular chips, and unstable crack propagation. The finite element model has demonstrated the feasibility of brittle cutting simulation with some limitations applied. There are 4 different results when using the original scale and the scale that limits the deflections to be 51.2% elongation, 12.8 elongation, and 3.2 elongation respectively. These are the material responses to the cutting tool. The first is when the F is equals to 1, which is the original scale. The workpiece and elements experience excessive deformation. Many stretched cohesive zone elements remain alive through the chip has been distorted significantly. The second material response is when F equals to 0.08. Small but consistent chips generated from the shear plane, which is similar to the cutting of brittle metals like high carbon steel. The third material response is when F equals to 0.02. It begins to generate fragmented, irregular debris accompanied by dusty pieces which can be similar to ceramic materials. And the last material response is when F equals to 0.005. This is an extreme case where the workpiece shatters upon the tool contact. The next literature review is on the failure criteria and cutting force. Machining of titanium alloy was investigated by 2D finite element analysis performed to understand the effects of ultrasonic machining. Workpiece material of titanium alloy was modeled as plastics, and to observe the effect of failure criteria, conventional turning simulations were run with and without failure criteria. Serrated chip formation is obtained in simulations with failure criteria, while chip shape is smooth in simulations without failure criteria. Maximum temperature in ultrasonic assisted turning operations is observed higher by compared with conventional turning operations. The motion of tool retractions in ultrasonic assisted turning allows some duration to cool down for the tool cutting edge. Cutting force is reduced in ultrasonic assisted turning operations compared to conventional turning operation. This is the cutting force for conventional turning and ultrasonic assisted turning. As for the methodology, there are 4 main steps needed to be taken for this project. The first step is the research. The research is done by studying case studies and finite element modeling done by other researchers. The research is done to get the whole idea on how ultrasonic machining works and undergoing the process of machining using frequency and amplitude. The research is also done to enhance the knowledge on how to create finite element modeling and its functions, as well as the inputs and outputs that need to be considered and analyzed in order to achieve an ideal result of this project. The research is done by studying case studies and finite element modeling done by other researchers in finite element modeling of ultrasonic machining. The next step is testing the finite element modeling in Abaqus. For this step, Abaqus software is first needed to be installed and learn each and every function of the tools in the software. This can be learned through the internet such as Google and YouTube, where creating the finite element modeling is shown. During this step, it is important to take note on a few aspects which is vital in creating a finite element model, such as learning on how to insert the suitable input parameters such as material properties, which will affect the finite element model simulation results. The steps needed to obtain the output of the simulation, such as the cutting force, is also needed to be learned in order to obtain the intended result. Next, we move to the third step, which is to create the finite element model. For this step, it is vital to know the input parameters needed for this project, such as the material properties of the workpiece, because the success of the finite element modeling simulation depends on the input parameters as well as to get the desired output, such as the cutting force and chip formation. So for this step, it is crucial to determine and insert suitable inputs such as material properties, mesh elements, and boundary conditions. When creating the finite element model is a success, we can move. The next step to be taken is to analyze the data. The output data are then analyzed by referring to the research paper and also through the internet by comparing the data obtained with the data from the researchers. Once the finite element modeling simulation succeeds, the output data of the simulation, such as the cutting force and chip formations, are recorded to determine whether the objective of the experiment is achieved as well as to determine whether the problem for this project is solved. The output data are then analyzed by referring to the research paper and also through the internet by comparing the data obtained through the finite element model simulation and the research papers online such as YouTube and Google, where it is reliable and accurate. For the expected results, there are two main results is to be expected in this project, which is the chip generated during the simulation and the cutting force obtained from the simulation. The first expected result is the chip formation. Chip generation during machining is a material removal process in which the workpieces material are removed in the form of numerous tiny chips. So the expected result is also when the tool is able to cut the workpiece without causing any crack or damage. As you can see in the figure shown, the tool is able to cut the workpiece without causing any crack or damage, and the chip formation is also formed intendedly. The next expected result is the cutting force. Cutting force is the resistance of the material to the cutting tool intrusion. There are a few factors that will affect the cutting force results, such as the material properties, the depth of cut, selection of node points, and the velocity of tool when cutting. As you can see in the figure shown, the expected cutting force for this project. And this is the list of reference used in this presentation and the proposal. The first reference used is the finite element modeling of orthogonal machining of brittle materials using an embedded cohesive element mesh. The second reference is the social and behavioral science. The third reference is the effect of ultrasonic vibration on the turning process. The fourth reference is the cutting force model for rotary ultrasonic machining of brittle materials. And the fifth reference used is the engineering solution for mesh size effects in simulation of delamination using cohesive zone models. That's all from me. Thank you. For further information and inquiries, you can contact 013-447-2148, or you can email at irfanriaz79@gmail.com. That's all from me. Thank you, and Assalamualaikum warahmatullahi wabarakatuh.